All right, I think we should start. So let's finish up what we didn't get to last time. So just to remind everybody where we left off last time, we were discussing bad API design. And I mentioned a few examples of different types of suboptimal design decisions that one could make. So one of them was insecure defaults, requiring the user to go out of their way to set options to make an API work securely. The other one was confusing function signatures that do different things depending on the arguments that you pass to the function. And lastly, there was behaving differently based on functionarity, which is the number of arguments that a function takes. And we talked about jQuery as an example. Took all these different types and returned completely different objects depending on the type. And then in one case, there was even the first and the fourth case, you see here that both take in strings, but the last case is a HTML string, and it actually does something completely different based on whether the string you give it is HTML or not HTML. And then we talked about this express example, where depending on the number of arguments that you pass into the use function, you get completely different behavior. And then we came to the buffer class, and this is where we left, where we ended. And so just to review, the idea behind buffer was we need a type to represent binary data in Node. And later on, the JavaScript language ended up getting some built-in features that allow us to represent raw data and manipulate it. But Node still kept its buffer class because there's all this code written that assumes that buffer exists. And so in Node, you have buffer, and you have typed arrays and array buffers. And so this was the API for buffer, if you recall. So we have a whole bunch of different types we can take in. We can take in other buffers. We can take in arrays of where each element in the array is a single byte, so a number between 0 and 255. And we could also take in a string. And in the case of a string, it's basically just going to interpret each letter as a byte, and then put that into the buffer there. OK, and so we showed a demo where we implemented a server. And if you recall, the server looked quite reasonable. The goal of the server was to take data in and convert it to some other type, some other representation. So hex, base64, or UTF-8. And if you recall, we made the API a little strange in that we made it actually take, in the query string up there, you see it takes, let's see here, there it is, yeah. It takes a JSON string, and then that gets turned into a JSON object, and then we pull off the str and the type properties, and then use that to do our conversion. Does everybody remember this? OK, cool. So the conversion is done here, and all you do is you just pass the string into the buffer constructor, and then you call toString on it, and then pass in the type that you want to convert it into. So this can be hex, base64, or UTF-8, and a couple of other things. And then we just return that. Right, and so when we actually visited this server, we ended up doing something kind of like this. So we typed in a string like hello, and then we got the base64 representation of it. We can change this to hex. And so on and so forth. And then this is the surprising part. If you actually change the string to be a number, then you actually get back memory, uninitialized memory from the Node process. And if you switch it to UTF-8, you can actually see like bits of the memory right there. Cool. So I promised you that this time we would talk about how this happens and why this happens. And I'll do that now. So this was the code we wrote. And the important thing to know about the API, the buffer API, this is the problem. This is the crux of the issue. If you pass in a number, like I mentioned before, you're going to get that many bytes of memory. So if you pass in 10, you're going to get a buffer that's size 10 back. But for performance reasons, Node doesn't zero out the memory before it allocates it to you. So you can think of it like it's literally calling malloc and just giving you the pointer to that memory. And it's your job to fill it with zeros if that's what you want to do. OK, so you can see here, if we call new buffer and ask it for a buffer of size 10, and we do that 3 times, we're getting completely different values each time because we're just getting whatever garbage was in the memory at that time. And so the correct way to use this responsibly is to zero out the memory before you actually pass it back to the user. So if you know that you're about to fill this in with a string that's exactly length 10 and it's going to override all this, then you don't need to zero it out. But if you're unsure that you're going to do that, then you should definitely call fill 0 and make sure that it's full of zeros, and then you can safely sort of set a few of the bytes in there and not worry about the rest potentially being private data. So the reason why our API had this problem, though, is if we go back to the server code right here, this stir variable isn't necessarily a string. We're in JavaScript, and so the types are sort of, there's no type enforcement. And so the question to ask is, what possible values can get passed in here, and what are their types? And if you look where we call convert, we're actually just passing in data.stir. And data.stir comes from the JSON object that the user passes in. And so actually, the user controls the type of data.stir. So if the user were to pass in a number here instead of the string hello, then when we call json.parse, we're going to get back that the stir property is a number. So the user's in control of the type. And that's just one of the, that's just the way that JSON works, right? The user gives you an object, and it can have strings, and it can have nulls, it can have numbers, it can have sub-properties, which are objects, sub-objects, and so on. Does this make sense to everybody? Yeah, OK, so it seems like, OK, maybe one thing we could do to fix this is to just, ensure that the stir that we pass in is actually a string. So we could say, if the type of stir is not a string, then make stir into a string. This could work. And if we do that, let's see what happens to the API. Did everybody understand this? It's just converting it, just coercing it into a string. So if we go back now to the browser and we refresh, then what we've done is, even though we've tried to trick the server by giving it the number 100, the server said, no, we're going to turn that into a string. We're not going to let you make that a number. So this is one way to fix this. But the problem is just that, so so there's an issue that, there's an issue with this API design. Specifically, let's see, where I don't have a slide about it. That's a bummer. Actually, no, we can use this one. Yeah. So anyway, the point is that if you look at all the different ways that you can call new buffer, all of them are safe, except for the case where you call it with a number. So you can pass in completely untrusted user data into this constructor, and it's basically just going to take whatever that is and just allocate some memory and then fill in that data into that memory. Except for if you pass in a number. Then you have this sort of unsafe behavior where now the data that the user gave you actually causes you to produce this buffer full of sensitive information. And the best way to see how this is potentially dangerous is to look at this package here. So the WS package is a very popular NPM package that implements a WebSocket server. So a WebSocket server is just a way to accept sort of long-lived socket connections from a browser, and I guess we haven't really talked about WebSockets in this class. Who's familiar with WebSockets here? OK. You can think of it, it's similar to a TCP socket. So it's the level below HTTP. It's sort of computer A wants to talk to computer B, and so it makes a socket, right? One of the computers connects to the other computer. But this is implemented actually on top of HTTP so that the browser can use it. So a browser can make a WebSocket connection to a server. It uses HTTP. But what's different about it is normally in HTTP, you do a request, and you get a response, and then you're done. With a WebSocket, you just establish a connection, and now the connection stays open. And either side can send data whenever it wants to, and that connection lives as long as you'd like it to live. And so why do we do this? Because we want to have low latency communication. We don't want to have all the overhead of making a new connection each time. And so we just keep the connection open. And so that's what you use WebSockets for. But anyway, that's besides the point. The way you use the WS package is you create a new server, and then you can listen for connections. So this event will fire anytime a browser shows up and connects to the server. And And then we're saying, OK, anytime that the browser sends us a message, we're going to go ahead and parse the message, and then we'll echo it back to them. So this is like the hello world of WebSocket servers. If you look up WebSockets, this is the first thing that they're going to have you build. Basically, this is a server which receives the connections from browsers. Whatever the client sends, the server just sends it back. But we're also like checking the message type. So we're like, the message can contain a type and it can contain data. And if the type is echo, then we're going to be like, you want us to echo this back to you. So we call socket.send with the data that the client sent to us. So let's see here. So let me just show you what this would kind of look like. So if the client sent an object that looked like type echo data hello world, and sent that to the server, then the server would send back the string hello world. And that's basically what that server does, right? And so anyway, this looks quite safe. Right? I mean, this is a hello world example. This is an extremely popular package. But it turns out if the client is able to make data be a number in this example, then what actually happens is the server, when the server calls send, inside send, it calls new buffer and passes in this data into it. And if the client makes it a number, then it's going to produce a buffer that's a completely uninitialized memory and then send that back to the user. And so basically, what this server actually does is now when I send it the message, if you go back to the thing I showed here, so now instead of sending it the data hello world, I'll send it the data 100. What the server is going to do is internally it's calling new buffer on 100, and then it's passing, it's doing some transformation to it and then passing it back to me. And so what I actually get here is instead of hello world, I get 100 bytes of memory, whatever that happens to be. And so I can just dump the server's memory by doing this, right? And it was surprising that this existed. It's pretty bad. And so the story here is I was looking. A friend and I were working on a node package together, and we noticed that our code was vulnerable to something like this. And the package we were specifically working on is one that does BitTorrent, the BitTorrent protocol. And so BitTorrent is a file sharing protocol. You connect to a bunch of random people that you don't trust. They send you messages. You send them messages. It's a very it's a very networked and chatty protocol, and you connect it. Like basically anybody who wants to connect to you can connect to you and send you stuff. And what we were doing was we were doing something kind of like this. We had a bug kind of like this, where if somebody sent you a message and it was a number instead of a string, and we expected it to be a string, then we would just go ahead and send back that many bytes of memory to the user. Who sent that to us. And so random people on the internet could basically dump our process's memory. And we were like, whoa, this is bad. It turns out it was actually kind of hard to exploit. And you can only get 20 bytes of memory at a time, but it was still bad. And so we fixed it. And then we were like, this seems like a thing that a lot of other people might also mess up on. And so we started looking, and then we found this one in WS, and we found a bunch more. And so what we did was me and Matthias reported it to Node after we fixed it in our own package. Oh yeah, I guess this is what I just said. So yeah, you could send a message and get back 20 bytes from the process's memory. And this is the commit where we fixed it. And you can see it's quite an easy fix. But basically, we had this helper function here called, let me make this a little bigger. So we had this helper function here called ID to buffer. And this takes in like a peer ID, which is a string, although it might be a buffer. And so what we were trying to do was like, OK, so we were trying to convert potentially this string into a buffer. But if it's already a buffer, so if buffer is buffer, then we just return it as is, because it's already a buffer. We don't need to do anything. Otherwise, we assume it's a string, in which case what we were doing was calling new buffer and taking that string in and saying it's a hex string, and then this turns that hex string into a buffer, basically, right? So what we needed to do is make sure the type is actually a string before we do this, because if it's a number, then we're vulnerable to this issue. And then otherwise, we're just going to return null and then handle that case up there. Does this make sense? What the fix is? Basically, we really have to make sure that a number isn't passed in here. So yeah, so we fixed that, and then we found Yeah, so we fixed this we privately told the folks who maintain WS about this issue, and they talked about it here and fixed it. And then after we did this, a bunch of other people started looking for these bugs and found them like everywhere. There was this one guy who wrote like a static analysis tool as a ESLint plugin, and he just went around and like running this on all of the packages he could find, and it was really kind of noisy. It was printing out all these false positives, but he sorted through all of them and found a bunch of issues. And like one of them was in the request package, which is incredibly popular. And actually, wait a minute. I think I found this one. Sorry, so he found other ones. Yeah, I think yeah, this one was me. But yeah, the way this one worked was basically, so request is just a package that makes it a little bit easier to send HTTP requests. And so one of the things you could do is you could send like a post request to this URL, and you could attach. This is like an attachment. If somebody clicks in their browser, they click to select a file, and then they submit a post with an attachment. This is kind of effectively doing the same thing. It's making a post request with this like file attached. But if the file that you're attaching, the data that you're attaching, is a number, then what's actually going to happen is you're going to attach 1,000 bytes of your own memory and send it to the server. And so there's no proof that anyone was like using this wrongly and was vulnerable, but it's a bad API design if you just pass in the wrong type and suddenly you're just like owning yourself. And so we opened this issue and we gave them an example of sort of how to cause the problem, and they fixed it. And again, it was a really simple fix. So if we look at the files that were changed, it's like literally, like if it's a number, make it a string. Like, yeah. And then this is a package that some of you might have used on assignment 0 to handle binary data. And this one also, same problem. It was vulnerable to the same thing, and it had an easy fix again. Just if it's a number, make it a string. So anyway, the point is this was pretty pervasive. So I wanted to talk a little bit about like ideas for how we could prevent this. So obviously we mentioned one is like you could just sort of reject numbers. So buffer. Oh no, this is actually different. So you could say if you pass a number in to buffer, we're just going to say you can't do that. Like this is not something we want to allow. So we kind of showed that here, except here we just turned it into a string. We could have just thrown an error, and then this wouldn't have happened. Another idea is we could validate the JSON. So there's a package that you can use called JSON schema that's getting quite a lot of popularity, and there's a spec around it. And the way it works is you sort of describe the shape of the JSON that you want to accept. You say, like, this field is supposed to be a number, and this field is supposed to be a string, and this field is supposed to be an object that's supposed to have, and so on and so forth. And you can run an untrusted JSON blob that the user gives you through that, and it'll tell you if it matches the correct shape. So that's something you can do. The downside of validation, though, like this, is that if the user gives you an object with extra properties in it, and you validate it, it's not going to complain that there's extra properties. So the way the validation works is it just checks the properties that you asked it to check. And if there's extra garbage in there, then it's not going to check it. And so this can lead to issues where let's say you add a feature to your API endpoint. So now you expect the user to be sending you additional properties. And then your server code starts to use those properties, but you forget to update the schema that you created. And now you have a problem where you're not validating that one field anymore because you forgot to update it. So a better way to do this would be to define a class. You can just make a class, like make a new class in your project, and then have it take in the constructor this JSON object, and then basically look at the types, basically look at all the properties that you expect to be there, and then ensure that they're correct type, and then create like getters and setters on the class that expose the data, and just the data that you want to expose. So that's one option. And then lastly, we could just fix buffer to be less error prone. Like it shouldn't be designed like this. It shouldn't be such a potential hazard to the users. And so, to summarize the main problem, it's that the data that gets passed into buffer is often untrusted user input. And if it's a number, then you have this really bad information exposure. And we have this design where the default, the common thing is unsafe. So you're getting back this uninitialized memory as the default behavior. And it would be better if we zeroed the memory out for the user so that they can just pass in a number and not worry. The sort of argument against doing that by the Node project was that this would be slow. It actually slowed down making buffers by like 25%. And so that was unacceptable to them. They're like, Node is all about performance. We can't do this. And so I would still argue that the default should be safe. And if a user wants to sort of opt out of the safe behavior and say, give me uninitialized memory, I really know what I'm doing, trust me, then they should be able to do that. But the default should be the safe behavior. And so we argued for that. But then another just even bigger issue is just that we have these two different kinds of functionality mixed into the same API. Like, if you pass it any type except a number, then you're going to basically be converting that data into a buffer representation. But if you pass it a number, you're allocating a buffer with that much memory, and it's uninitialized. And that's like just two types of different functionality. They should just be in different APIs. Like, they don't need to be all jammed into this one constructor. And so I think that's actually the best solution. And so that's what we argued for, and that's what they ended up doing. So now the way you create buffers is you use these three APIs. So you do buffer.from if you have any type and you want to convert it to a buffer. You use alloc if you want to allocate memory, and that allocates safe memory, so it's zero filled. And then lastly, if you really know what you're doing, then you can do alloc unsafe, and you'll get the old behavior of uninitialized memory. So anything that's performance sensitive, where they don't want to zero it out because they know that they're planning to overwrite it themselves with data, they'll use alloc unsafe. But yeah, this is a wild pull request. Or issue, I guess. We opened this up, and there was huge discussion about it, like thousands of comments, and it's just it took a little bit of convincing, but in the end, I think this is a much better design. They ended up deprecating the old buffer design, so if you use that now, you get a printout, a warning printout, which is discouraging people from using it. The problem was, though, for many, many years since this happened, this was like, I guess, in 2016 or something, or 2017, I mean, there's so many NPM packages that are using the old behavior. Like, this is just a very common thing. So pretty much every package was doing this in some way. And so it was not possible to like easily switch people over to the new behavior. And so this was also complicated by the fact that a lot of times these open source packages want to support multiple versions of Node. Because if you're a library author, you don't know what version of Node your users are going to be using. The developers who are using your library, you don't know what version of Node they're going to be using. They could be using the latest one, or they could be like 2 versions behind. And you want your library to work on as many versions as possible. And unlike when you're an app developer, you can just decide the version of Node your app is going to use, and that's the version you use. So because of this, library authors were sort of hesitant to use the new APIs, because if they did that, they would be basically telling all those users on older versions that you can't use this library anymore. And so one solution to that was we created this shim library called safe buffer, which you could use. You could basically import this package, and this package would give you the new APIs even if you were in an old version of Node, by basically just simulating, doing the same thing that Node is going to do for you. So you could sort of safely, even in old versions, you could safely use buffer. But yeah, this took forever to percolate through the whole ecosystem. And yeah. And at first, they wanted to print out this deprecation message right away to tell everybody, like, this old behavior is unsafe. But the problem with that was that literally, if you did that, every single time you ran any program in Node, you would just get a deprecation warning. Like 100% of programs would just print this warning out because everyone is using new buffer. And so the decision was like, well, we shouldn't print this message out. It's just people are going to be seeing this message for like 2 years in a row, like until it finally gets updated. We can't do this. And so they deprecated it in the docs and not at runtime. And then we just waited basically for people to eventually update everything. And a bunch of people started sending pull requests to all the different projects, and it was a very slow process. But now you do get a deprecation warning. Anyway, so I think this is a cool little story of bad API design. And then I found one other one that I wanted to mention. Actually, before I move on, any questions about the buffer stuff? Cool. OK, so then there's one other example that I found when we were talking about bcrypt for the password and authentication lecture. And while looking at the docs, I noticed that they do the exact same thing that the buffer was doing. And so even a security-sensitive library like bcrypt makes a similar mistake. And so what we can look at is this function here. So this is the function you use to hash a password. So the user gives you their password. You're going to hash it before you store it in the database, because that's what you do. Remember, we had this second variable called hash rounds, which is the number of times you want to apply the hash function. And we do it multiple times because we want to make it slower for an attacker to iterate through our database and try to basically undo the hash function for our users. And so this is supposed to be a number like 10 or something, right? But what happens if this is accidentally a string? It does a completely different thing. So if you make it a number, it's going to use that as the number of hash rounds, right? If you make it a string, it's going to assume that you've already selected a salt for your password, and you want it to not generate the salt for you. So normally, internally, this thing is going to generate a salt, add it to your password, and then hash it 10 times, right? But if you make this a string, it's like, you don't want me to generate a salt. You already have a salt, and I'm going to use that, add it to the password, and then hash it, I guess, the default number of times, maybe one time, right? And so what you end up doing is if you accidentally make this a string in your code base, all of your users' passwords in your database will have exactly the same salt. It'll be like the string 10 as the salt, which completely eliminates the value of a salt, because the point of a salt, if you remember, was what was it? It was to make sure all of your users' hashed passwords couldn't be attacked all at once. You want to be able to basically iterate through to try to reverse the hash for a single user at a time, and that's what the salt lets you do. So you might ask, well, how could you, this is your code, you're writing this, you're the developer, why would you pass a string into this, right? This isn't untrusted user input. It's not exactly the same as the buffer case. But I would argue that this is the kind of thing where it might be coming from like some configuration in your application. It's common to have important parts of your application configurable via like a config file or environment variables. Who's used environment variables before? Knows what those are? So an environment variable is like a sort of a variable you can set in your terminal, and then whenever you run a program, and that program can just look at the environment variable and sort of change its behavior based off of that environment variable. And it's often used to store sensitive information like keys to connect to AWS or whatever services you're using. And so you might put this in an environment variable, and guess what? Environment variables don't have types. They're all strings. Every environment variable is just a string. There's no like differentiation of, this is a number. And so if you're using process.env.hashrounds to get your hash rounds value, then you'll now be passing a string into here. This is just one example of how this might happen. Does this make sense? Anyway, I just think in general these types of things should be separated into different functions, and that's what this is supposed to demonstrate here. Cool. So just a few more little things you can do on your server. One thing is you can hide errors, detailed stack traces from your users. This is nice to do because when a user looks at a stack trace, if they're an attacker, they can figure out the exact paths that all your files are on, and so they can figure out, like the user is named Faraz, and like the app is running inside of this folder here, and look, they're using Express, and maybe they can figure out the version of Express based off of the name of the file if that had changed in a different version. And so there's all this information they can learn about your application that you would probably rather them not know. So hiding this kind of information from users is a good idea. One way to do this is in your error handler. You can say, if we're running in production mode, then we want to make our stack trace nothing. And so don't print out any stack information on the error page, but otherwise print out a full stack trace, because this means we're developing our app and we would like to be able to see the stack trace. Another thing that you need to question? Yeah.
Is there any way to maliciously and remotely modify the environment variable?
I don't think so. I mean, and what do you have in mind? Like, how would that happen?
I'm just thinking like how it would be more secure than, for example, because I suppose that if you like literally stored the key on the disk, then an attacker could just like go and grab it somehow. But having it in an environment variable would put it behind like authentication.
So I mean, if the attacker is running, if they somehow can do like a code injection and actually run code on your server, then they can read the environment variable just as easily as they can read a file. Yeah, I actually don't know how much better an environment variable is than a file. environment variables are standard practice for whatever reason. That would be interesting to look into. Like why exactly is an environment variable better than a file? Well, one reason why a file is usually bad is because people will check it into their source control, and so then the file will end up on GitHub, and then now you have your key like in a repo, and if you accidentally make that repo public, or if it's an open source repo, then you have problems. Yeah. Hmm?
Wait, so in the case where you're working in a team, how do you share environment variables? Let's say like what's the best way to do that?
Yeah, that's a good question. So typically, I think people will put the key directly into the interface for their hosting provider. They'll have some way of sort of like typing it into a website or something, and then the hosting provider will make that environment variable available, and it'll only be there in production. So like your local developers, they'll have to use a completely different key for a completely different database. So that way, all the developers in the company don't have the key that is the key to all of your users' data. You know, if you don't want one person's stolen laptop to compromise everything, that's typically the way it's done. Yeah. Okay, just like I think I have like one or two more before I'm going to go on to the new stuff, the new topic for today. So one thing that servers will often do is they'll reveal the name of the server being used for vanity reasons mostly. So if you use Express and you look at all the responses that the server sends, it attaches this header x powered by, and so you can like basically figure out any site that's using Express by looking at this header. And you might think, well, what's the big deal? I mean, so what? A lot of people are using Express. It's not that big of a deal. And it probably isn't a big deal, but in general, why make the attacker's job easier? The less you can tell them about what you're doing, the better. And so, you don't want to rely on this like for security. You don't want to be like, they don't know that I'm using Express. Now I can, but it's still easy. It's still harder for the attacker to figure out what's going on your server if you don't tell them the exact software you're using. And there's an even worse example of this, which is for Nginx. Actually, it's not showing it here, but I think Nginx by default includes the version of Nginx that's being used as well as the name. And so with that, you actually end up telling the attacker the exact version you're using, and if they know that version is vulnerable, because say Nginx releases an update, right? And they say, we fixed a really bad bug. Everybody should update. An attacker can say, well, wait a minute, who's still running the old version? They can write a bot that just scans websites. It just crawls the internet like Google or any other search engine would do and look for sites that return a header that contains the vulnerable version. And they'll just do that until they find a server that's running the vulnerable version. So you don't want to be advertising the version you're running. And you can turn that off in Nginx with the parameter server tokens off. And then you can also, the other thing to worry about is if you remember the way Express was advertising itself. So typically, you'll run Nginx in front of a server like Node, or in this case, PHP. So you have like a proxy, basically. Nginx is a proxy. And so what's going on here is the Nginx server is advertising that it's Nginx, but then behind the scenes, your actual app that's written in PHP or Node or whatever is also advertising itself as well. So you want to turn both of those off so that the attacker doesn't learn anything. And one other kind of wild example of fingerprinting is, so this is fingerprinting a server. You can actually fingerprint the operating system that the server is running on as well. And so even if you turn all this stuff off, they might be able to figure out you're running Windows version whatever, or Linux version, like Ubuntu version whatever. And the way that an attacker can do this, and I don't have any advice for how to prevent this, but if any of you have heard of Nmap, Nmap is a network scanning tool. And you can point it at a server that you want it to fingerprint. And it'll figure out what operating system that that computer is running by sending it a packet, getting back like a response, and then looking at the white space in the response. So different operating systems will have like subtle things that they do differently that don't affect the behavior of the network protocol because it's spacing or something like this, or ordering of headers or ordering of different things. And basically, they built in a giant rule set here where they can guess the operating system of a machine as long as they can get that machine to send them a packet. So you would run this on your computer, you would point it at like a server, and then it would send the server a packet. And of course, the job of a server is to respond to clients that show up. So the server will send you back a packet, and then this will analyze that and predict, make a good guess for the operating system that it's running. And so you can use this to basically find people who are running unpatched versions. Like if it can tell you, oh, they're running this operating system in this version of it, you can use that to potentially attack that server. So Yeah, it's fingerprinting for servers. Who knew? Yeah, so I don't know actually a good defense against this, but I thought I'd just throw this out there. This is not exactly web security related, but it's quite interesting. Yeah, so some lessons, just to review the lessons we talked about before. Complexity is the enemy of security. Explicit code is better than clever code. Fail early, and code defensively. And now I'm going to go on to the new topic for today, which is local HTTP server security. So we're going to talk about servers that you run locally on your computer, either when you're developing an app, or there are actually programs on your computer that are running local HTTP servers right now. And there's a huge number of security risks that arise because of that. And we're going to talk about one example of that in depth now. So, but first, I just want to mention this is the most dangerous code that you run every day on a regular basis. And I think I mentioned this last time, but if you forget to pass a host name as a second argument to listen, then you've basically told your node server to accept connections from all interfaces. So all interfaces means anybody who can send a packet to your computer, your server will get that packet and then respond. And so what this means is that if you call this, what this means is that basically anybody on the same Wi-Fi network as you can connect to your machine if they know that you're running a server on this port, right? And so this is a common thing that all developers do, but it's actually, I think, I'm surprised there haven't been more issues relating to this in the wild, because if you're working on some like super sensitive application for some company, right, and you just start up your little development server and you let anybody in the coffee shop connect to your server, they can learn it. I mean, they can see the website that you're developing before it's ready to be released, right? And so, I mean, that's bad. And on top of that, if there's any vulnerabilities in that server, they can use that to attack you, right? So you might be in the middle of developing something, it's not quite finished, you haven't really added the security checks yet, and while you're working on that, somebody in the same network as you sends you an HTTP request that compromises your machine, right? And that's not something you're thinking about when you're developing a local app. So I just think it's surprising that this hasn't been more of an issue. But anyway, this is the correct thing to do if you're developing, is just to say, I only want applications on my own computer to be able to connect to this server. And so that way the browser that's running on your machine can connect, and other applications on your machine can connect, but other people on other machines can't connect. Does that make sense? OK, so that was just a little example, but now this is the main thing we're going to talk about today. So who has heard of Zoom? It's a conferencing application. OK, so most people have heard of Zoom. Zoom meeting, it's a very popular video chat application. A lot of businesses use it. And earlier this year, this security researcher discovered a zero-day in the software that allowed any website on the internet to turn on your webcam and just get a feed of you without you interacting at all, just by visiting a website. And the way it worked was that the Zoom software, it was running a server on your computer, and it allowed any site on the internet to send it requests. And those requests, there was one request you could send that would basically turn on your webcam, join you into a meeting, and it would be the attacker's meeting room, when the attacker could just sit there and see who's joining. You get like a ton of people joining. In fact, in this blog post that they wrote about the issue, there was a link where they're like, oh yeah, that's the other thing too. They gave the company 90 days to fix the issue, and they didn't fix it within 90 days. So they just said, OK, and they pushed publish on the blog post that explained exactly how to do it. And there's a link in the post that anyone could click, and it would join you into this blogger's chat room. And so while this was like going viral, when this post came out, there was just like hundreds of random people who were reading the article who clicked the link, and there was like a big party chat room of like all these people who were like, "Whoa, it worked! Hi, everybody!" So yeah, pretty funny. But Zoom has like a ton of users, and I guess it was the Mac client only, they said, so it was only Mac users that had the problem. But yeah, so they estimated it was like 4 million users who were affected by this. Yeah. So we're going to talk a little bit about it. These are some quotes from the post that he wrote. So he says, the vulnerability allows any website to forcibly join a user to a Zoom call with their video camera activated without the user's permission. On top of this, the vulnerability allowed any web page to DOS a Mac by repeatedly joining a user to an invalid call. And additionally, if you've ever installed the Zoom client and then you've uninstalled it, you still have a localhost web server on your machine that will happily reinstall the Zoom client for you without requiring any user interaction on your behalf besides visiting a web page. This reinstall feature continues to work to this day. So that's the worst part. You could literally be like, I'm fed up with Zoom. I'm going to uninstall this garbage from my computer. And then you uninstall it, and it's secretly keeping this local HTTP server running on your computer. And this server is the thing that had the vulnerability in it. So even if you're not using Zoom anymore, you got rid of it a year ago, you're still vulnerable to this issue because of the way they designed this. Yeah, so just a few more quotes from his post. So let me start off by saying having an installed app that is running a web server on my local machine with a totally undocumented API feels incredibly sketchy to me. Secondly, the fact that any website I visit can interact with this web server running on my machine is a huge red flag for me as a security researcher. Having every Zoom user have a web server that accepts HTTP GET requests that trigger code outside of the browser's sandbox is painting a huge target on the back of Zoom. So do y'all catch this part here? So the interesting thing about the way that these local HTTP servers work is it's not just that when you're listening that any app on your computer can connect or other users on your network can connect if you configure it that way. But it's also the case that, so say you're smart and you say, OK, I'm going to make this server so that only apps on my own computer can connect, so other people in the coffee shop can't connect. Well, there's still a whole bunch of applications on your computer that might be able to connect. And one of them is a web browser. Your web browser is visiting random untrusted websites. Those untrusted websites can send GET requests to localhost 4000, as an example, right? It's just another server. It's on another origin, sure, so you have the same origin policy to contend with as an attacker, but we know there's all kinds of requests we can send even though the same origin policy is in place. It doesn't prevent all kinds of things, like it doesn't prevent GET requests, for example, right? So basically this local server is accepting GET requests from any site on the internet. And so this server better be secure because any site can just send it a request, and if that request triggers code execution or joins you to a meeting or whatever, then that's just going to be available. That's going to be functionality that's accessible to any site that you visit. Does that make sense? Yeah, so it's pretty wild. So I was going to just do a little demo of this in action. So this is a little server here that I'm going to make a server on my computer that listens for connections, and you'll notice that I've made the server so that it's only listening for connections from apps on my computer. But what I'm going to make it do is I'm going to make a server which, if you send it a request, it will open up the dictionary. So this is very similar to what Zoom was doing, but it's a little bit more, well, it's kind of useless, but it'll give us the idea of what we're trying to do. So this is a server. So here's the command I'm going to run. And if I just run this command in my terminal, you'll see that it just opens up the dictionary. So that works. OK, so what we'll do is we'll make a server that listens on the home page, and it will, whenever someone sends us a GET request to the home page, we will execute the command. And you'll notice I'm not taking any user input here, so this is relatively safe in the sense that I'm not like running the command the user sends to me. I'm just running this exact command here verbatim to open the dictionary. And then once that finishes, either it succeeded or it didn't succeed. So we'll say that if it errored out, then we'll send a status code of 500, which indicates a server error, and then we'll send let's just send the stack trace back to the user, even though I just told you not to do that. And then if there was no error, then we'll set the status to 200 and we'll send success. Cool. OK, so now if I go to my browser and I visit localhost 4000, actually I need to start the server up. So let me just go here and start the server up. OK, and then if I visit localhost 4000, wow, it opened up the dictionary in my computer. So basically, it's sending a GET request. So there's a server running on my computer, and if any app on my computer sends it a GET request, the dictionary will open. Does this make sense? Yeah. So so one question you might have is, well, OK, so who can send these requests, right? So who is allowed to send a request to this server on my computer? Well, let's go to example.com, and I'll open up the console, and this will simulate. This is code running in the context of example.com. And we'll see, can example.com actually send a request to this server? So if I just call fetch, that will hopefully cause a GET request to get sent, and what do you know it does? So any site on the internet now, as I'm browsing around, can just pop open the dictionary on my computer if they know that they can do this. They know that they can send a request to this server. Any questions about this? OK, so one thing you'll notice is that the console is telling me that access was denied. It's saying that access to the fetch at localhost 4000 from the origin example.com has been blocked by Core's policy. So why did it work, even though it's saying that it was blocked?
Because like before you send this like GET request, you'd never even know if there's going to be an access control or an header. So like you have to send it anyways. Like if this header is not present, it just block the reading, but like it's sent anyways.
That's exactly right. So what's going on here is that the browser is denying me the ability to read the result of the request, but it still let me send it. So I sent the GET to the server, and the server sent back, what did it send back? It sent back the string success. And I wasn't allowed to read that string. But it still had to send the request to the server, get the response back, inspect the headers, and see, is this site willing to let anybody read its response? And the answer is no, and so it's denying me the ability to read the response. So another way of putting this is if I were to make an image tag on the page, and I were to make the source of that image be localhost 4000, then of course I'm not going to get any errors, but the thing's still going to open. So basically, if I embedded an image in the site, the image would load with, I guess it wouldn't load because I'm sending back the string success. That's not really an image, but yeah, it would cause the GET request to get sent and this app will open. So we can fix the error by sending an additional header. So if we set access control allow origin, and we make the value star, now we're saying that basically anybody can read back the response from this request. And so now when I run that code, it launches it, and there's no errors. And if I really wanted to, I could actually read the response out by awaiting the result of this, then getting the text value of it, and awaiting that, and there you go. So I got the response string success. But it doesn't matter. The point is, even if I can't read the response, I can still cause the request to get sent and trigger this. OK. So that's how a random server on a random site on the internet can write JavaScript code that interacts with a local server on your computer. Yeah.
Would there be a difference if you made the same request from the terminal, like from the terminal?
No difference. Yeah, no difference. I'll show you right now. We can do that. So I'll do curl. Can everybody see this? Curl localhost 4000. Same thing. So any app on my computer that is allowed to use the network can send a HTTP request to this server on my computer and cause it to behave this way.
So what if you didn't allow the access control origin? Can you still get the error that was there before?
No, you can't read the response value back if you remove the header. Yeah, but you still cause the dictionary to open because that happens regardless of the header. Any questions about this? Does this make sense? OK, so this is kind of like what the Zoom server was doing. Is running a local server. And this is something kind of interesting. So if you want to see sort of how vulnerable you are to these kinds of issues, you can run this command here. And what this does is it lists open file descriptors that are running on your machine. Or sorry, it'll list open file descriptors that the processes that are running on your machine are using. So if you've ever taken CS110, you'll know about file descriptors. File descriptors are just like handles to files or to sockets that processes are using. And so these are, and I filtered it by ones that are listening. So this is only going to show me listening sockets. In other words, these are web servers running on my computer that are listening for connections from anyone. And so you can see here, I'm running two servers at the very top there that are, the process is called rapport D, which I looked it up. It turns out that if you do man rapport D, it enables phone calls that go to my iPhone to end up ringing my computer. So basically, when my phone gets a call, it will connect to the server running on my laptop on port 55220 and tell my Mac that I have a phone call, and it will forward like the voice data to it, something like this. That's what this server is used for. There's also Comm Center, which I also looked that one up, and I think it's related. So it says it provides functionality to allow phone calls to be made and received on the Mac. So basically, these 3 servers right here are running to support that feature of my Mac. And then lastly, oh look, there we go. We have a node process that's also listening. That's the one that I'm running right now. And you'll notice something. So the handoff server is listening on star colon and then star colon, which means that anyone on the local network can connect to this. So any of you can connect to this server. So I hope that their security is good, and I hope that they're validating all the messages that you're sending to it, because any of you can send packets to my computer on this server right now, and it will be processed by the code that Apple wrote. So there better be no bugs in it. But you'll see here the node server that we're listening to is only listening on localhost, so you can't send packets to it. But that's the way you tell how those sockets were configured. Okay. So there's a whole bunch of servers running on your computer. There was one really bad example of a local server that was running on folks' computers. There's this antivirus company called Trend Micro. And if you installed the antivirus on your computer, it would install a local HTTP server. And this server was vulnerable to RCE, or remote code execution, from any site on the internet. So what this means is, I'll go to this issue here, we'll look at it. It's a wild. This is a Google Project Zero issue, which means that some security researchers at Google found this bug and notified the company. And so basically, with these 3 lines of code, actually you could turn this into 1 line of code, because this is just a fetch, but he's using an older API that does the same thing as fetch. But basically, if you can cause a GET request to go to this URL, and you're running this antivirus on your computer, so any site on the internet could just send a GET request to this URL, localhost 49155/API/open URL in default browser, which is supposed to just, I guess, pop open a tab to this URL. But they made a lot of mistakes. One is they let any site send GET requests to this. Secondly, it turns out the URL can be a program on your computer, and it'll just execute it. So the way that they show, typically the way that security researchers will demonstrate remote code execution is they'll just pop open your calculator on your computer to indicate that, like, look, I could have opened up anything, but I'll just open up the calculator to be nice to you. I could have owned you, but I didn't. And so, yeah, this code here could have been embedded in any ad or on any site that anybody visited running this antivirus, and they would have been instantly, like, the computer completely compromised. So yeah, local HTTP servers are dangerous. If you write one, you're basically allowing the sketchiest ad and the sketchiest site on the sketchiest corner of the internet to send you requests, and if you did it wrong, then all of your users are owned. So try to avoid writing them if you can. And you can look through sort of, the cool thing about Google Project Zero is that when they notify the company about the issue, they post it into this Google repo, basically, this issue tracker, and the company representatives can respond, and this is all private. But then once 90 days have gone by, they just make it public. So you can see all the interactions between the researcher and the company, and you can get an idea about how seriously companies take security. And it gives you a sense for sort of their internal processes and how urgently they resolve these issues. And so you can see, I don't think we have too much time to go into it here, but you can see the researcher, like at one point he gets frustrated and he says, where is it? He said, hey, I just wanted to check if there's any update here. This is trivially exploitable and discoverable in the default install and obviously wormable. In my opinion, you should be paging people to get this fixed because they weren't going fast enough. Yeah, and anyway, it's fascinating. If you have time, look through Google Project Zero issues. You can learn a lot by looking through it. Yeah. Anyway, so back to Zoom though. So there were problems with Zoom's local server. So the first problem was that any site on the web could send a GET request to the Zoom server running on your computer and then join you into a conference room. And the conference room number was controlled by the attacker. They could join you into their own room. The other big problem was that they let the conference host decide the policy for whether the participants' cameras would be turned on by default or not when they join the room. So the attacker would just say, yeah, in my conference room, the rules are everyone who joins has their camera on when they join, no permission prompt, and that would just be the policy. On top of that, like I mentioned before, if you uninstall Zoom, then the local server would remain installed on your computer. And the reason why they did this, they say, is that if you uninstalled Zoom and then later on somebody sent you a Zoom link, you could click the link and then it would hit the local web server on your computer and tell it, go quickly reinstall Zoom for the user. And then, so even if you uninstalled it, you could click a Zoom link and it would just open up like it was never uninstalled. That was their idea. And then lastly, it was vulnerable to a denial of service, where a site could just sort of make your computer completely unusable. So I'm going to show you a little bit more about these things. So this is the control where the host of the meeting could specify whether the participant's video would be on or not when they join. So it was just a UI control. And then this is the code to sort of basically freeze the user's computer. So the way this worked is you would pick a conference room number that didn't exist, and then you would send a GET request to this URL. So the local Zoom server, and then you would say launch, join a room, and then the room number would be that random invalid number. And you would do this in an interval, like as fast as you can. And every time you do this, the focus gets taken away from your browser, and Zoom sort of launches and intercepts focus. And then when you do this again, it does that again. And basically, doing this fast enough just causes your computer to be completely unusable. You can't focus anything else. You can't stop anything. You can't do anything or stop it from running because this is running too fast. So that's pretty annoying. But yeah, so after this post was written, they were like, this is actually fine. This is totally fine. And they defended their decision until the next day when they admitted that they were wrong and decided to remove this local web server. So I think they didn't realize the scope of the severity of it until the researcher went public with it, and then a bunch of their customers and a bunch of other people started contacting them, letting them know how serious the issue was. So this is how they tried to clean up the mess. So they issued an updated version of the app, which when installed would go and uninstall the local web server from your computer. And they also added a UI prompt to confirm that you actually want to join a meeting before you join. And problems with this are that users who didn't open up the app for a while wouldn't get the update. So they would still be running the local web server and be vulnerable to this until they finally had time to open up the app and let the install happen. And then lastly, the users who uninstalled Zoom, they would have no way to even know that this was the thing because they already, they're not using Zoom anymore. They're not customers anymore. So they'd be running this vulnerable server and they'd be stuck with it unless they happen to hear the news. So this is really bad. There's millions of people who were affected by this. And so, and this is the best part. So all this so far was just about sort of getting the user's camera to turn on. The researcher was trying really hard to find if there was an RCE, like a remote code execution here, where a site could actually just, like the other example I gave with Trend Micro, they could just run code on the computer. And he couldn't quite find it. But a week after he wrote his post, another security team said that they were working on in a similar part of the Zoom code base, and they found RCE. So if you combine the two things together, you actually would have this remote code execution that affects millions of people. So yeah, it was a week after, and then this other team basically wrote about it, and it was a zero interaction remote code execution. So this is what it looked like. If you went to a malicious site, you would just visit it, and then it said your meeting will be starting soon, and then now they're running code on your computer. And in this case, they just opened the calculator and said hello to you. But yeah, yeah. And this is like every person who was running this on their Mac was vulnerable to this. Yep, pretty wild. So then what happened? This is where the plot thickens. So later that same day, after this team wrote about the RCE they discovered, folks realized that Apple was silently uninstalling the Zoom server from everyone's Macs. And first of all, this is a little bit surprising because I think a lot of people didn't realize that this was even a functionality. This is a feature that Apple has. But it turns out, yes, there is a thing called the malware removal tool that's built into all Macs. And the way it works is it periodically pings an Apple server and fetches a list of bad executable files. So it has like a fingerprint, effectively, for executable files that Apple doesn't want any Mac to be able to run. And so it periodically fetches this list, and if you have a program on your computer that matches this fingerprint, then it will kill it and it won't let it run ever again. And this doesn't require your operating system to be updated. Like, this is a thing that's periodically checking in the background. So if there's an urgent program, urgent piece of malware that is a piece of malware that is spreading fast, they can sort of urgently stop it from spreading by just sort of basically blacklisting that program from running on anyone's Macs, even without an operating system update or a restart. And so that's what they did here. They basically uninstalled it from everyone's computers. Yeah, no update required, and it saved a lot of people because I think someone must have told them that there was an RCE here, and so they were like, okay, this is worse than the original security researcher thought. We need to basically kill this before it affects all of our users. So yeah, that's what Apple did. Yeah, okay, so I guess I already showed this. But yeah, so one thing I wanted to mention too was that, oh, wait, that was out of order. Okay, whatever. Yeah, so this is sort of the flow of how this all happened, just in case this helps to see it visually. So this is your browser. This is the server running on your local computer. So both the browser and the server this is your machine, your laptop. So you visit this join URL that's zoom.us/j/123 to join the conference room 123. It sends back a page. Once the page is loaded, then the Zoom page sends a request to the local server asking it to launch the room, and this request is initiated by the JavaScript code that's running on this page that came back from the Zoom server. And so that will cause the local server to launch the Zoom app and sends back OK to your browser. And I wrote opaque response here because this doesn't have a CORS header. It doesn't have that access control allow origin header. And so this page can't read the response, but it doesn't matter because the Zoom app was launched and that's all you were trying to do. So that's OK. But that's the flow. And one of the things they did that was kind of funny is they did actually want to be able to have the local server indicate to the page here whether or not the Zoom app was actually launched or not. But because it was this opaque response, this page wasn't allowed to read that value. And they seem to not be aware of the fact that you can use this access control allow origin header, to just say, for the local server to say, hey, I'm OK with the zoom.us, the page at zoom.us, being able to read the response. But they didn't know this, it seems like. So the way that they implemented this hack around the same origin policy is they had this response be an image, and they would vary the size of the image based on the message they want to indicate. So if it was a 1x1 pixel image, then this page could look at this, could sort of figure out the size of the image based on how it affects the layout of other items in the page, and be like, oh, the app actually launched successfully. And then if it was 1x2, oh, we have to go download the app, and all the different pixel sizes basically indicate different responses. So I don't know why they don't know about CORS, but yeah, not a very encouraging sign. Yeah, so basically, this is what they could have done if they knew about CORS. So then this is basically the same flow. The only difference is that when the request goes and the app is launched, the response just includes some JSON saying, hey, it was successful. And then you just have to put a little header here saying, I'm OK with the zoom.us reading this response, right? And so now they don't need to do that hack. Of course, this is still vulnerable to the main issue, which is that any site can still send this request. So we haven't fixed the problem. We've just removed this hack here they had. And of course, yeah, so we're relying on the browser to look at the header here and then to compare it to the page that we're on and then to decide whether the origins match and whether to allow the page to read it. OK, so this is the flow for the attacker force joining the user into a call. So the browser would visit the attacker's site. The attacker sends back some HTML code. The attacker's page loads. The attacker sends the request to the local server. And the local server launches the Zoom app and sends back this opaque response. So and then of course, yeah. So this is sort of the attacker flow. And if we throw in that CORS endpoint, if we use CORS, this doesn't solve the problem. I just want to emphasize this. So if the response that comes back contains this access control allow origin header that says zoom.us, the browser is going to say, is the code that's running zoom.us? And no, it's actually attacker.com's code that's running here. So it's going to deny this origin from being able to read the response. But it doesn't matter because we still launched the Zoom app. Okay, the attacker can't read the result here, but it doesn't matter. Okay, so let's see how we can fix the issue. So the easiest and best solution would be they should just not do this. There's a better way to cause a website to open an app on your computer, and that's to register a protocol handler. So Zoom can say, we are going to create the URL zoom:// and they can have their app register that, and then when you click a link that starts with that, the browser will ask the user, hey, do you want to open up this app on your computer to handle this? That's the best way to do it. But let's assume that for some reason you have a good reason to actually keep a local HTTP server. Let's say that there's no other way you can solve this problem. You must do this. You must figure out how to secure it. So let's talk about, can we secure this? Can we figure out how to make this local HTTP server actually secure? So some ideas. What if we, let's see here. So we could say we're going to require the user to interact before we join them into a call. OK, so when they go to a zoom.us link, we're going to have a little button that says, do you want to join? And then on top of that, we're going to ensure that our local server only lets zoom.us communicate with it. So now random ads and random sites you visit can't talk to the local server. So how do we do this? So let's have the local server inspect the origin header. That seems like a good approach, right? OK, so let's look at the flow now. So everything's the same as before. But now, when we make a request to the local server, I'm going to include these extra headers that are attached by the browser. So the first one is host. Don't confuse host and origin. I'm putting them both here so that you see them both, but they're very different. So host is the way that you indicate what site you're trying to talk to. Remember? So we're saying we're connecting to localhost 19421 here, and indeed that's who we're connecting to. And then origin is which origin triggered this request, right? OK, so because this was initiated by zoom.us, that's what you see in the origin header. And then now the local server can have some logic that says, is the origin Zoom? And if it is, then it can launch the Zoom app and then go ahead and send back a response to the page. And then, of course, we can read the response there. So this is one approach. Hmm?
Couldn't an attacker site just lie about the origin, or is that a browser-controlled thing?
Yeah, so that's a good question. So the origin header is one header that you can't control as JavaScript code running in a site. So that is always set by the browser to the true origin that initiated the request. There's no way to lie about it. Yeah. Now, if we were using the terminal and we were writing a curl command, of course we could put whatever we want in there, right? But because this request is coming from our web browser is guaranteeing that this is set to the true origin.
So the attack is still vulnerable if some attacker were running curl.
Yeah, but the thing is, yeah, that's correct. So if you're running an app on your computer that wants to talk to this Zoom server, then it can. But presumably that app could already just own you because it's already installed on your computer. So we're not worried about that case. But yeah, that's a good point. Yeah. OK, so let's see how if an attacker tried to join us into a call, would this approach protect us? So now we're getting our page from the attacker. The attacker sends the request to the server, and because this is initiated by the attacker, the origin header is set to the attacker origin. And so when the server checks, it won't match, and so it will just close the socket. It won't even send a response. It'll just act as if the server's not there. Let's just close the connection. So this page can't learn anything at all about our local server. Does that make sense? OK. So that kind of works. There's some problems with it, though. So one is that the browser doesn't always add this header, and this is so frustrating. So if you're sending what's called a simple request, which is the kind of request that it will be triggered if you are using an image tag or an iframe tag to load an image or an iframe from another URL, then the browser is like, this is a simple request. It's a GET request, and it's for an image, and you're not even going to look at the response. So this site doesn't care about the origin. So it doesn't attach the origin header. The idea is that any site can send these requests, and your server doesn't care to distinguish which origin initiated it. I think that's the idea. And so anyway, you can't learn the origin in this case. Also, if you're using the fetch API and you're making a request to your own server, then that's also considered a simple request because it's a site talking to its own same origin server, so it doesn't even bother to tell the server the origin. It's just assumed that it must be the same site making the request. OK, so this is not good. So what is the solution potentially here? Well, maybe let's just say, look, what if we say if the request doesn't have an origin header, we'll just block it, and we'll force the user to we'll force the page to include the origin header by making the request a complex request. And then if we require that, then we can just basically look for the origin header and check it. Does that make sense? OK. Another idea is you can change the endpoint to require a pre-flighted request. We'll talk about that in a second, what that is. But if you do that, then you can basically force the origin header to always be sent. So let's talk about this for a second. So just to emphasize, so simple HTTP requests are requests that are gets, heads, or posts, and they must have no custom HTTP headers set. And if it's a post, it has to be one of these three types here. OK, so what is the big idea here? This is all a lot of details, but the way to think about this is a very simple idea. OK, what are the types of requests that a site can make without JavaScript? So a site can embed an image to another site, right? That will make a GET request to the other site. A site can submit a form. Can make a form in HTML, no JavaScript required, right? So I can make a form, and when you click submit, it's going to go to this other site. OK, and those types of requests fit this criteria, right? A GET request, that's simple. A post that is a form submission, and these are the three types of, you can change the way the form is encoded, but it doesn't matter. The point is, they're the three types of ways you can send a form to a server. So if it's a form or it's an image or something like that, the browser's like, this is simple. Like you could do this without JavaScript. There's no harm in letting this go to the server. There's no damage that this request can do because this is the way the web has worked from day one. Sites have always been allowed to do this. So it doesn't bother to even attach an origin header or to do any kind of extra checks, right? So that's an idea. That's a simple HTTP request. So what is a non-simple one? We call those pre-flighted requests. And the reason why we call them that is because before we can send these more complicated requests to a server, we actually have to ask the server for permission before we send the request. And can anyone think of why? Why do we need to do this? So say, OK, here's an example. Say I have a delete. And the method is delete. You know, it's one of the HTTP methods. There's get, post, blah, blah, blah. One of them is delete. So when the server gets this delete request, it's going to delete some item that is specified in the URL, right? So if the browser were to let that request go through, and then the response comes back, and the response says, this origin is allowed to do deletes, it's too late. Like, the browser has already sent the request, the server's already processed the delete, and your response asks the browser to please not let that happen. It's too late. We need to actually we need the browser to sort of prevent this request from even going through until we've told it that it can. Does that make sense? Certain requests are so destructive that we can't let them happen. We have to actually ask for permission before we even send them. So that's what's going on here. So let's look at what would happen if the browser did not pre-flight these requests. So let's say you visited an attacker's site. The attacker sent back an attack page. OK, so now the page loads, and now they're going to send a delete request cross-origin to a site, victim.com. OK, and because of the way cookies work, blah, 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 the cookie is attached. And so the server is going to say, OK, time to delete item 42. That's what this request told me to do. And then it'll send back a response and say the page was deleted. And say that we try to enforce that only victim.com can send these requests by including an access control allow origin header. That's not going to quite do the job because, sure, I mean, yeah, this header will prevent the attack page from reading the response because this is saying only let victim.com read the response. And of course, it was the attacker that initiated this, so it can't read the response. But the damage was done. The server saw this, deleted the item, damage is done, right? So we can't do this. This is not an acceptable design. And so what we need is the options request. So this is another HTTP method like get, post, put, delete, etc. It's called options. And the way it works is the browser sends options first to ask for permission before it sends a pre-flighted request, so a complicated request. So if the server doesn't know about options and it gets an options request and it says nothing, then it will be the browser will interpret that as it being denied, the request being denied, because the server doesn't even know what an options is. Or if the server doesn't want to support pre-flighted requests, then it can also just not respond or send back an error. And then the browser will go ahead and deny that request. So let's see how we can use this to protect our local server. So remember, when the user is joining a Zoom call, we're going to now make our local server, instead of checking for the origin header, we're going to use this pre-flight technique to protect our server. OK, so what are we going to do? So the client goes to the Zoom site, gets back to the Zoom page, and now the Zoom HTML is going to send a request to the local server and say, please open up the app and join the meeting. And what we're doing, though, is we notice when I made the HTTP method, I made it put. Did everybody see that? So put is one of the ones that is not simple. Put is, it's not get or it's not post. So it's not simple. So this is a pre-flighted request. When the browser sees this, it's going to say, wait a minute, this server might not want a random site on the internet to send it a put. So let's ask if this is OK first. And so what's going to happen is the browser, before this request goes out, the browser blocks it. And well, first it asks the question, is this request going to the same origin? And of course, because this request is coming from Zoom, it's the Zoom HTML, zoom.us HTML that's active here, and we're connecting to localhost, which is a completely different origin. The browser's like, wait a minute, this is a cross-origin request. So it's going to say this is not the same origin. So we have to ask for permission before we send this request. OK, so I couldn't fit all this here. So this is the same browser as up there. So now what the browser is going to do is on its own. You didn't write any code here. This is not written by the developer of the Zoom site. This is the browser on its own. It's sending an extra HTTP request. And it's asking the server, is it OK for me to send a put? Will that be OK? So the way it does that is it says options. And it says the origin that's sending this put is the Zoom origin. And we would like to put, please. OK, so this request hits the server. And if the server sees it and knows what to do, it'll say, wait, so do I want to let this origin put to me? And because it's zoom.us, we'll go ahead and allow it. And so we send back an empty response. It doesn't matter what we send back in terms of the content. All that matters is that we say allow put. And so now the browser is going to say, OK, the server's fine getting puts, so let's go ahead and let the request go through. So it'll go ahead and actually send that put up there that it didn't send the first time. And then when the server gets that, now it has a much greater guarantee because it knows, OK, puts can only get sent if they were pre-flighted by the browser first, and the browser had to check with me first. And so this server is like very confident now that it got this put. It doesn't even care really what the origin is because it knows that a previous options request must have happened and it must have validated the origin at that point in time, or else the browser wouldn't let this go through. And so now we launch the Zoom app and we send back our success response, and of course we let the page read it by using that header. Does this make sense? So this is called pre-flight requests or options requests, and this is what we do for anything that's a complicated request. Thanks for bearing with me. This is complicated. I know it's coming at the end of class, so you're all probably kind of tired. But yeah, so last thing I want to go through is just what would happen if the attacker tried to pull this off. What would actually happen? How would the local server protect us? And as you can guess, it will once the attacker's code actually starts to run and it sends this put, the browsers are going to do the same thing as before. It's going to say, wait a minute, this is a put. This is not a simple request. So I need to ask the server first. So it's not a simple request it's not a simple request, and it's also not going to the same origin. So it has to check first. So it produces an options request, sends it to the server. The server says, is this coming from Zoom? And it's actually coming from attacker.com, so no. And so it sends back access forbidden to the browser. And now the browser doesn't even try resending that request up there. It's going to deny it because it knows it didn't get permission from the server. Yeah. So how much do we have left here? Oh, I guess we have like 2 slides. So I'll just go through it. So anyway, so this has protected our local server. It's allowed our local server to distinguish requests from zoom.us and those from other random sites. However, other native apps running on our computer can still talk to the local server, as I mentioned. So curl, anything running in your terminal, apps on your computer, they can obviously set whatever headers they want. This is because the browser is enforcing that sites don't tamper with the origin header. But a native app like a Node script or a Python script or something like that can obviously just make a request and set the header to whatever they want and pretend that they're coming from Zoom, of course. So, okay, so now you understand this concept. I'm glad we all talked about pre-flight requests because it would be sad if you made it through web security class without knowing how this works. And so this is actually really useful. This lets you protect your site in the real world. But because we're using this on a local server, I'm sad to say that there's actually another problem that means that our server is still vulnerable to every single website on the internet that wants to attack it. I'm sorry to end class on such a disappointing note, but next time we'll discuss an attack called DNS rebinding that basically lets any site on the internet pretend like it's the same origin as the site that it wants to talk to. So attacker.com can basically pretend that it's zoom.us and talk to this local server. This only works against local servers. So unfortunately, all of our defenses, all this stuff is still vulnerable to DNS rebinding. So we have to learn about DNS rebinding. So I told you local servers are really complicated, and you should be very scared and paranoid if you're making one. And this is why. Even after all this, we're still vulnerable. It's very sad. Yeah, so next time, come back, we'll talk about DNS rebinding. Thanks.